Hello. Today's video is about spontaneous imbibition. I'm going to explain the process physically, but I'm also going to describe it mathematically, and I'm going to present a semi-analytic solution for spontaneous imbibition in one dimension. An analytical solution has only recently been recognized and established in the literature. But let's start with a physical description. We'll have my piece of rock here. Okay, so here you have a dry piece of sandstone, so it's full of air. Okay, you could imagine instead that it contains some initial water and oil, but the air is the non-wetting phase. Okay, now we've got a glass of water here. Okay, and the water is the wetting phase. The rock, okay, the rock surface is mainly quartz. It likes water. It has an affinity for water. And so water will naturally move into the rock through capillary forces. So let's see what happens when we do this experiment, okay? Here's my piece of rock. Now what I'm going to do is I'm going to put the piece of rock into the water like this, okay? Okay, you can see it's almost surrounded. Okay? And you can see, if you look very carefully, there are a few bubbles that appeared. Okay, so the water now imbibes into this rock. And it does it spontaneously in the sense that I haven't injected water into the rock. But the rock, if you notice now, is a darker colour. It's got saturated, okay, with water. It hasn't quite got completely saturated right at the top. But if you allow time, actually the water will go all the way, even beyond where it's actually been physically dipped into the water here. And you can also, it's quite difficult to see, there are a few bubbles that come out, and those bubbles represent the air that's been displaced. Okay, so that's what I mean by spontaneous imbibition. Maybe not the most clear demonstration on this video, but that's a process that occurs naturally in lots of different situations. Yeah, soaking water into a tissue, baby's nappies, and we also see it, of course, in oil recovery when we have a fractured medium, where we have a body of rock that gets surrounded by water, and then the only mechanism by which the oil can be recovered is a spontaneous imbibition process. So let's now try and approach that problem mathematically. So for that, I can show here on the board. Okay, so what do we have here? If we look at the top left here, we have a situation where water, indicated by the blue arrow, will imbibe into a piece of rock. And the non-wetting phase, that can be air, that can be oil, actually comes out in the opposite direction. So if you imagine one-dimensional flow, not necessarily where it's completely surrounded by water, but we're going to solve the equations in one dimension. So we consider one-dimensional flow, and in fact, we just consider effectively an infinite one-dimensional system. Okay, so whatever goes in comes out in the other direction. And so in terms of the mathematics, we can say that the total velocity, qt, is 0. Okay. Now it's driven by capillary forces. So I've drawn the capillary pressure here, and I've drawn the capillary pressure, quite a general capillary pressure, for a mixed wet system, and this is important. So we're going to start in the rock at the initial water saturation, low water saturation, and the water saturation increases as more water moves into the porous medium. If it's a mixed wet rock, the capillary pressure can be both positive and negative, shown by the red piece. Spontaneous imbibition is such that we only imbibe without forcing the water in. So we get to a capillary pressure of 0. So the end state will be a water saturation that I've indicated as SW star, which is when the capillary pressure is 0. It doesn't go to the residual oil saturation, and that's really rather important. Okay, we only imbibe in the water wet regions of the rock. So a rock that's been in contact with crude oil and had its wettability altered, okay, we can only have this spontaneous imbibition to fill those pores that remain water wet. Okay, we're also going to ignore gravity. That actually is a reasonable thing to do if we're looking at relatively small regions of rock up to about 1 meter in extent. Okay, the gravitational force is small. So if we go back to some of the equations that I presented previously, and I'm just going to leap in and give you the equation. I'm not going to derive it, but we had an expression for the water velocity that had 3 terms. One was a vection, where you had a term that was proportional to qt, or qt0, so that goes. The second was a gravitational term, which I've just said we're going to assert correctly, actually, that it's a small effect. And so what we're left with is the capillary pressure term. And the capillary pressure term can be written like this. This is the permeability, and these are the mobilities. That's the mobility of oil, the water, oil, and this is the total mobility. And mobility is simply the relative permeability divided by viscosity. And then we have a capillary pressure term that I'm going to write like this. It's a dpc by ds, dsw by dx. So it in fact is a gradient of capillary pressure. It's the gradient of capillary pressure drives flow. And we know this from Darcy's law. It's a gradient of pressure drives flow. And because this is driven by capillary pressure, it's going to be a capillary pressure gradient. So in previous videos, we have derived this rigorously. Okay, this hasn't just appeared out of nowhere. The governing partial differential equation, again, that we derived phi is the porosity. SW is clearly the water saturation. Okay, there's a time dependence here, and then we get dQW x equals 0. Now this can be written, if you notice this is a d by dx of this, which also has a d by dx. Okay, so we can write this equation as follows. Okay, and we assume that the porosity and permeability are constant. You can write this as ds by dt equals d by dx of some quantity which I'm going to call d, and it's a highly nonlinear function of saturation. Okay. So I'm difficulty writing. Okay, so what do we have here? So D is in fact a capillary dispersion. So let's just look at the mathematics first and then explain it. So D is a nonlinear function of S. If you just go through the equations, there is a minus sign here because we put it over the other side. So it's minus K over phi. Okay, it's minus K over phi. And then you have here the mobility of water, the mobility of oil divided by the total mobility. And then you've got this derivative of the capillary pressure. Now, D itself is a positive number. Don't get fixated by the minus sign there. Okay, it's a positive function. Why? dpc by ds. Okay, and this function is negative, right? It has a negative value. The mobilities are always positive. They can be 0. They're obviously 0 at the end point. For instance, the mobility of water here at the end point is 0. Okay, so D is a function of saturation, but its value is either 0 or positive. Okay, it's not negative. Okay, so we have this equation. Now, the first thing to do is, rather than getting fixated with mathematics, is actually to look at it a bit more physically. This is a time derivative and 2 spatial derivatives. So for those of you who are familiar with partial differential equations, if instead of S, for instance, we had concentration, this would look like a diffusion equation. Okay? And in fact, although water doesn't diffuse into the rock in a literal sense, it's not driven by some random motion, it's driven by a capillary pressure gradient. Mathematically, it can be described as being a diffusive process because the equation used to describe it is like a diffusion equation. Okay. You get exactly the same equation if we look at pressure response in single phase flow this will be a derivative, time derivative pressure. And again, you get a diffusion-like equation for pressure. Okay, and again, it's not because literally it's diffusion in terms of a random motion. It's just mathematically you have this. And you have this because the flow, right, is driven by a pressure gradient, and then you've got a d by dx of the flow. So you get a second derivative emerges on the same naturally. Okay, so this is a diffusion type equation. So how are we going to solve this diffusion type equation? Okay, now there were going to be two tricks for solving this equation. Okay, so I'm going to introduce the first one, and because I need some room on the board, I'm going to remove everything now except for the equation we're really solving, which is this one. Okay. And if you don't mind, we can even remove the schematic here. Okay, so the first thing we're going to do is do a variable, right? Look at the right variable. Okay, so the analogy is always going to be with Buckley-Leverett. So with Buckley-Leverett, we looked for solutions that were a function of velocity, x over t. And the reason is because we were looking at an advective process. We were sort of going with the flow. This is a diffusive process. So if we have a diffusive process, we know that the distance you move scales as a square, the distance you move goes as root t. To go a given distance takes a time squared. Okay, so the variable to look at, we can call it w or omega, depending on what you like. Okay, we write w, okay, is x over root t. And we're going to look for a solution where S, the water saturation, is just a function of this W. So it's very similar to Buckley-Leverett, where instead we did X over T, but this is a diffusive process, so we can't, X over T isn't going to work. Okay, and this is your trick number one, but it's actually relatively standard. There's nothing special about this, and this has been understood for a long time. This is how you deal with diffusive processes. Okay, so now we now need to do the separation of not separation of errors. We need to transfer this equation into an equation for W. Okay, so let's go through it. This is relatively straightforward mathematics. Okay, so you've got a ds, okay, by dt is, okay, dw by dt ds w by dw. Okay, and this you can differentiate, right? So you get minus a half t to the 3/2. So this can actually be written as minus w over 2t, okay, times ds w. And then we'll do the same with the x derivative. Okay, so and this is easier, by dx is just 1 over root t. Okay. Okay, so that's straightforward. So now what we can do is we can transfer this equation into an equation with w. Okay, now the only other thing is we got two x derivatives here. So ds by dx is 1 over root t. But notice this is a d by dx with a partial derivative, so it's taken at constant time. So the time can go out to the front here. It doesn't appear in the derivative. And then we're differentiating again by x, so we get another root t. So we're going to get 2 root t's here. So we're going to get a 1 over t here. Okay, so let's erase, let's give ourselves a bit of space to actually do this. Hopefully we can erase all of this. Yeah, okay, good. Okay, so now what this equation is going to become, okay, so we got the d by dt, so that's minus omega or minus w. As I said, it's up to you. over 2t. Okay, you've got dsw by dw. Okay, and then this is 1 over t, because they're 2 root t's, of d by dw of d. Okay, ds by dw. Okay, so that's the equation you end up with, and that's relatively standard, and you can see that it's going to work is because the t's cancel. And if we tried another variable that would say just x over t, it wouldn't work. Okay, so this is why you can do this as a diffusion equation, because actually there is these t's disappear. Okay, so what I'm going to do now is I'm going to try and integrate this equation. Okay, and I can integrate it once quite easily, because what I'm going to put is I'm going to put dw up here. Okay, so these dw's essentially cancel, and we got a d here. So if we stay in red, right, it's as though we're going to cancel this, and then I'm going to integrate this. Okay, okay, so we can see this. If I integrate here, this is d, little d, big D ds by dw, so that the integral of that is just what I have there, okay, just by definition, right, because this is d of all of that, okay, and then I've just got this minus w over dsw, so I've got that integral. Okay, so if we rearrange things, and now what I'm going to do is I'm actually going to erase this transformation of variables, because it is, I have to say, relatively standard. Okay, this is how you deal with a diffusion equation. So that was, so the first trick was this use of these variables, but that was relatively straightforward. And so what we end up with now is we've got sorry, let's put it in black. Okay, so what we have here is minus, right, the integral of w dsw equals, and I'm going to put the 2 over here, it's 2d dsw by w. And of course there'll be a constant of integration, but we're going to consider that later. We can consider that still somehow, I would say, wound up in this one. Okay, so that's where we end up. Okay, so lots of people have got to that stage in the derivation. It's relatively standard. But where you get stuck is that d is a nonlinear function of saturation. Okay, so this is relatively standard mathematics, but you're sort of frozen at this point. However, what you have to do now is introduce the second key trick. So this separation of variables, I'd say, is idea number 1. But idea number 2, which is the key one, and this is McWhirter first proposed this in 1970, and he's a hydrologist. Sunadra and McWhirter wrote a paper in 1990, which more or less outlined this solution, but it was done in a really hesitant way, as though it was a sort of special case, and sort of try and ignore it, please. It wasn't later until Schmidt and Geiger at Heriot-Watt University had another look and realized that this was a general solution. And what it is a general sort of Buckley-Leverett type solution for imbibition, right? And it's very clever. And so what's the idea? Well, the idea is this. It says, we know in Buckley-Leverett you have a fractional flow, and you know that the solution is the derivative of the fractional flow. So let's do the same here. Let's define a fractional flow, which I'm going to call f, which is a function of water saturation. And what we'll do is the fractional flow will be what you might expect. That at the initial water saturation, it's 0. At the maximum water saturation we're going to get in the system, which is SW star, it's some maximum value, and you can normalize it to make it 1. Okay, it's going to be some maximum value. Okay, and it turns out that this fractional flow, if it's normalized, so f star is defined to be 1, so you divide it by its maximum value. Turns out that this fractional flow physically is indeed going to be the genuine fractional flow. It's going to be the fraction of the flow compared to what it is at the inlet. So the water imbibes fastest at the inlet, and obviously there's less and less imbibition as you go along. And if you're a long way away, obviously there's been no imbibition. Okay, so in fact this fractional flow is the fraction of the imbibition relative to what it is at the inlet. Okay, why? Because at the inlet the saturation by definition is SW star. So at the inlet, right where it's begin to imbibe, it's at the maximum saturation. As we go further into the rock, you go down to the initial water saturation. Okay? So I'm not going to actually show that. I haven't got enough time mathematically to go through the details, but essentially that's what it represents physically. And then the solution, when I just said it's sort of Buckley-Leverett-like, is omega is df by dsw. Okay. So we're just assuming that. Okay. So what can we do? Well, we've got a partial differential equation here, so maybe we should, well, let's differentiate it, shall we? dw by dsw is d2f by dsw squared, which I can call, if I want to, I can call that f double prime. Okay, so let's see where that's got us. Well, actually, it's got us a long way, right? Really very quickly, because let's have a look at what we had at the top. Okay, okay, we've got w dsw. W dsw is just df, so we've got minus the integral of df. Right? If you can't see this, w dsw is here. That's just df. Okay, is equal to ds by dw. What is the inverse of dw by ds? So it's 2d divided by f double star. So I think we can integrate df, can't we? Right. So suddenly everything is becoming very easy. So we can write f is minus 2d, right, over f double star. And just a moment, we do need a constant of integration now. We've done it twice, okay? So people might be getting a bit nervous. But actually, we defined at the initial water saturation, okay, f is 0. But also this diffusion coefficient, the dispersion coefficient, if you remember, had these mobilities, and the water mobility is 0, okay? So when f is 0, d is 0. Okay, so we don't need another constant. So we end up with this equation. And I'm going to show that in red, because that actually is as far as we go. Okay. And then what you could write, if you're going to do this formally, and I'm just going to, this is not terribly rigorous sounding mathematics. Okay, so let's look at the red equation. So it's a really bizarre equation. I don't believe any of you have seen anything like it before mathematically. Okay, so it's a nice new application. It's this fractional flow, f double primed, is minus 2d. Now, that actually is a semi-analytic solution. You might say, well, it doesn't look like it because I haven't got an equation for f, right? If I have got an equation for f, I can find w, right, just by differentiating it, and I know that as a function of saturation. Okay, so it's a bit unsatisfying. Formally, we can write f as this double integral because f double prime is this, so I just integrate 2d over f twice. But just I can't integrate 2d over f twice because I don't know what f is. But actually, it turns out with a bit of mathematical manipulation, you can turn it into one integral. You can integrate by parts essentially, and it's just one integral. And then what do? You guess f, you evaluate, you know d is related to the fluid properties, highly non-linear, but it's related to the fluid properties. You know it if you've measured the fluid properties. So you know d, you guess f. I mean, let's say f is just linear function of saturation, for instance, begin with. Evaluate the integral, find a new value of f. Put that new value of f back in the integral, and you iterate. And is this something weird and unstable? No, you iterate 2 or 3 times, you get f, to within 4 significant figures. Okay. The other way in which you can do it is numerically. This is actually, an ordinary differential equation we have here. Okay, so you can solve this as an ordinary differential equation quite readily. So what you do is you start off actually at SW star at your F star, and then you basically step backwards, and you find at the initial water saturation, do you actually reach 0, and then you adjust your F star until that happens. So both if you do it with an integral or with a difference equation, you have to have an iterative process. But it's something that anyone on MATLAB or a spreadsheet could probably code up in an afternoon. Right? So it's not analytic in the sense I don't have F equals equation like I do with Buckley-Leverett, but it's semi-analytic in the sense that it's an ordinary differential equation. I can just solve that reasonably straightforwardly to machine accuracy on a computer with no problems. And that's different from solving the original partial differential equation that's a function of both distance and time. And it turns out when you try and solve it numerically, you might say, well, just do it numerically normally. That's what most petroleum engineers say. You know, put it in Eclipse, that will give me the right answer. Well, actually it won't. It turns out you need to use hundreds of thousands of grid blocks and super tiny time steps. And the reason physically is the whole thing is controlled by this F star, which is the initial imbibition rate, right at the inlet. And a numerical method where you do it in grid blocks, the very first time step it gets it wrong, and then the whole thing is wrong. So you need a super duper refined grid in space and time to get accurate solutions. Whereas this solution is actually a refined grid in saturation space. It's relatively straightforward. So I'm not going to say any more about that at this stage because that's the mathematics. Okay. But what I'm going to do, because it's a little bit unsatisfying to sort of leave it there, is let's actually show some example solutions. Okay, so for that, I've got some slides. Okay, so here, so this is spontaneous imbibition. Okay, so let's just go through the physics so you don't get lost, right, in the mathematics. It's a diffusive process. Okay, what that means is the distance the water travels and the recovery, right, because how much oil comes out related to how much the water's gone, scales as the square root of time. So if it's Buckley-Leverett, it's linear. I'm injecting something. If I keep the injection rate constant, in a year I produce so much oil. In 2 years I produced twice as much, assuming we haven't produced anything at the well. But it's basically a linear. It's a velocity. It's scaling with time. This is scaling with root time. And as I said before in a previous video, there are basically only two things that happen. Either things go linearly with time, or they go as the root of time. I suppose there are other processes that go exponential, and it's clearly not an exponential process, right? Those are really the types of behavior. It's not every case is something mysterious that you have to overthink, okay? So the time to imbibe a given distance scales is the square of that distance. So here's my schematic again. We got the rock sample, okay? Water is imbibing inwards, QT is 0, so the volume of oil escapes. This is the governing partial differential equation, okay, written out far more nicely than it was on the whiteboard, where D is this capillary dispersion, okay, and I've left out the phi, actually. This isn't correct. I don't think I can annotate this, but actually there should be a porosity term here, okay. The way I've done it. If you leave out the porosity term, then you just keep the porosity in all the equations. So it's not necessarily a mistake. This is correct, but I've kept the porosity in before I had the porosity term actually subsumed in D. It doesn't matter which way you do it. Okay, so let's actually look at some solutions. Okay, so again, these are solutions from my book shown here. And we did this for Buckley-Leverett. So we've got our relative permeabilities: strongly water-wet rock, weakly water-wet rock, and a mixed wet rock, and an oil wet rock. Well, there's a cross through the oil wet rock. An oil wet rock, the capillary pressure is always negative. There is no spontaneous imbibition. It repels water. So end of that discussion. You have an oil wet reservoir, spontaneous imbibition, I'm sorry, it just doesn't happen, okay, unless you push the water in which case it's not spontaneous, okay, by definition. Okay, so let's look at this. For the strongly oil wet rock, what we've shown is D, okay? So this D function starts off at 0, and then at the end point, where we end the imbibition, is actually also the residual oil saturation, where the oil is no longer mobile, because everything's water wet. So this D function goes up, reaches a maximum, goes down to 0. Okay, so it's highly nonlinear. There's one funny curve here. This is the Van Genuchten curve. For those of you who are not hydrologists, in hydrology, people tend to use multi-phase flow properties, particularly capillary pressure, and the relative permeability of water. It's related to a model developed by Van Genuchten. The Van Genuchten model is rather strange. It actually has an infinite capillary pressure gradient at the endpoint. And so, in fact, their D, rather than going down to 0, actually diverges. Okay, so it's a different model. Okay, I'm not saying it's right or wrong, it's just a different model. Universally used by hydrologists, whereas in petroleum engineering, we use different models, which actually give you very different imbibition behavior. And that's something that no one's really got their hands on and explored, because mathematically, they're really very different. Okay, weakly water wet and mixed wet cases, the residual oil saturation is where you actually have to force the water in. So the capillary pressure is negative. So the D function ends at a finite value because at SW star, when you stop imbibing, both phases are still mobile. Okay? So for a weakly water wet case, you see D goes up and is sort of maybe beginning to go down. The M's here are the viscosity ratio. So an M greater than 1 is more viscous oil. So it's the oil viscosity divided by the water viscosity. A small value of M would represent, for instance, water imbibing into air or into CO2 as an example. Okay. So a mixed wet case is more interesting. The mixed wet case you see here, because you only imbibe sort of halfway through and just in the water wet regions, you see in the mixed wet case that D is sort of going up and is almost at its maximum at the end point. So here are the solutions. Okay, you can go through the mathematics that I've just shown. I'm not going to go through any more detail, but as I said, you know, it does require another step that's not very easy just to show in a video, but all the equations are there. Okay, so here are the saturation profiles. So these saturation profiles now, as a function of this omega or W, okay, x over root t. But again, a bit like the velocity plots, don't get yourself in a muddle about x over root t, v, right? For a given time, a snapshot, right? You know root t, so it's just saturation against x. It's just that saturation profile propagates not linearly with time, but as the square root of time, because it's a diffusive process. Okay, so here the strongly water wet case. The Van Genuchten model, because as you see, the D was big, the capillary dispersion was large. Okay, that means it's going to imbibe faster. And these, as they've got a scale, this is looking at a rock with a permeability of 1 Darcy and a porosity of 20%. So Van Genuchten imbibes very rapidly. And what you see here, which is rather interesting, is because you have an infinite dispersion actually at SW star, okay, you have a flat profile here that moves fast, right? It flats because it's infinite dispersion. At the endpoint, you see here at SWI, the dispersion coefficient is 0, so there's no diffusion. So the front goes in with a sort of sharp nose. It's almost a shock, but not quite. It's not quite, okay, because you can never really get a proper shock because it's a diffusive process, but the diffusion coefficient is going to 0. So it's sharp at the end. Okay. Weakly water wet case, for most of these models, what you see instead, because the diffusion coefficient is 0 at the, or low at the end point, is actually that you see a drop in the saturation. Okay. And then the mixed wet cases here, again, it's related to the capillary diffusion coefficient. It's 0 here. Here, what we're seeing is a large value. So actually at SW star, as we showed, it was sort of maximum. So it's smearing out most rapidly to begin with, and then sharpens down. Okay, but the point is the scale here. Okay, these values here are about 0.016, but this is 10 to the minus 4. It's 2 orders of magnitude smaller. So it's not that a mixed wet case imbibes less. In this example, it's imbibing up to about 60%, 50%. So the maximum saturation is lower in a mixed wet case, obviously. But the mixed wet case is slower, much slower. And the reason is physically that the water has to imbibe in at a low saturation. The whole process, the whole rate of the process is governed by the water relative permeability. And as we've discussed previously, and in fact was on those slides, is in a mixed wet case, at low saturation, the water relative permeability is very low, even lower than a water wet case. In a water wet case, at least the water saturation can get higher as we imbibe into the whole of the pore space. So in a mixed wet case, it's really bad. You've got a low water relative permeability at low saturation. Now you're confined to low saturation because you can never get to a high saturation because you can only imbibe in the few water wet pores. So you find that recovery is slower. And experimentally, the sort of experiment I did to begin with, right, my glass experiment, here it's nicely all imbibed, okay, that experiment you can do in the lab, and you can find that in a mixed wet case, the recovery rates are maybe 1,000, even 10,000 times slower than a strongly water wet case. Okay, and it's all controlled by the relative permeabilities. Okay, well, I'll stop there. This is a fascinating subject, and one, surprisingly enough, that people have only really understood rigorously mathematically, or at least been established in the literature in the last 10 years. Okay. There's a lot more we could say, but this at least outlines the principal pieces of mathematics and at least some of the solutions. So thank you very much.